participants, all the faculty members, students, and means all the participants from all over across the India. So just now, I Miss Arvind sir told me that from across the India, from all states, from all corners, participants are joining this session. So welcome all in this presentation, expert talk you can say, but I prefer to call this interaction session. So, but because whatever I am learning, and I am just giving, extending that learning, information, knowledge to other participants in the India, in other institutes. So welcome again. So I will take 1.5, you can say around 75 minutes for this lecture, and 10 to 15 minutes I will reserve for any question answers or interaction in the last. So we will start. So this topic, so we will start this. So this is SST or solid state transformer. It is not a new concept. Since last 4 years, I am working on this, and this is, as the name suggests you, solid state transformer. So it will use all the solid state devices like MOSFET, inverter, IGBTs, or diodes, or all semiconductor devices, silicon based, germanium based, or latest you can use that silicon carbide or gallium nitride, or you can say that wide bandgap devices. This SST, I will call from now onwards SST only. I will not take full name of this. So this SST, or you can say this as the PET also, power electronic transformer, or smart transformer, or some papers are also on intelligent transformer. All these four names are for the single device or converter, that is SST. So this SST for future renewable energy hub. So this topic I have selected for this just to cope up with the main theme of the FDP going on. So this is my presentation outline. I will first give you the what is the need of this SST and how it evolved, means its evolution from since its inception in 1971 around, and expectations from future electric vehicles and such highly nonlinear loads with RES infrastructure, and it is very non-predictable, you can say. So some is you can predict and something you cannot predict. So the demand prediction is required in implementation of any power electronic, battery storage, and RES type of infrastructure. So we will see what are the different expectations from future EV with RES support. Then I will just focus on different topologies and configurations of this SST. And then we will have some applications of SST, and then challenges which we are facing to implement this SST in future grid. And then I will just take a brief journey on this DAB, dual active bridge, a different topology, control techniques, and whatever work I'm doing here in my research lab with the students. So that I will share with all of you. This DAB is very important component of this SST. So now we know that in the traditional grid, this is the generating station. Okay, so I can use this highlighter. Not required. Okay. Okay, so in the traditional grid, this is the generating station, thermal, coal, or nuclear based, or any other source based generating stations. Then we have to step up the voltage to very high voltage, EHV or HV, then transmit the power to the local station or substations, and again stepping down the voltage to a lower level required by industries and some residential applications. So we can see that we have to use these huge transformers, all right, and its main function is that it will step up or step down the voltage, and at the same time it will isolate the two circuits, from generating to transmission or transmission to distribution side. So isolation and second, stepping up and stepping down the voltage. These are the main tasks it is performing. But in future, this is the practical solution for self-adaptable or self-healing electrical grid, in which you have to incorporate so many devices like IoT devices, smart communication, smart sensors, and different RES like PV, wind, fuel cell, battery management, also storage. And at the same time, you should be able to control the demand response, supply response, everything you have to control automatically using latest IoT technology. So this type of self-adaptable and self-healing electrical grid is not possible with such type of traditional transformers. If you will use these two transformers at low frequency 50 Hz with a very huge and bulky size, then in future applications like electric vehicle and space applications, defense applications, military applications, in those applications, you require two main basic objectives, and those are reliability and second, power density. So power density is the major concern nowadays, because you have to develop the converter or inverter system which will consume very less space and which will give you very high power also. So the power density is the major concern, and such type of transformers is a culprit. These are the devils in for future electric grid. So what is the need of this SST? Now we will come to that point. So this power density and reliability is the major concern, and so we have to reduce the volume of the whole system and increase the watt per inch cubic of the system to be developed. So basically these are the main advantage of this traditional transformer, because it is very highly reliable and robust also, and it will give you more than 99% efficiency, and it is relatively inexpensive as compared to other power electronic converters of the same ratings. But these drawbacks I have taken just to take care of the future need of electric grid, including EV infrastructure, RES, and battery storage management system, and such type of very non-linear loads. So now the need is that you have to interconnect your PV, wind, or other DC sources with the existing grid. You cannot replace the whole existing grid with the new DC grid as the scenario is changing. So to take care of this, there are no DC ports available in this transformer, no DC port available. So where you have to connect this PV and wind or fuel cell battery, you have to ultimately develop some DC port or DC bus, common DC bus at different DC voltage levels. So this is not friendly for a integration of RES and EV and storage. Second is it has no capability of voltage or frequency regulation. That means if you have to control the power flow, voltage and current and frequency as well, then you have to use some additional external equipments or converters which will take care of those requirements. And third one is the large weight to volume, means high power density, low power density is there. So these are the three main weakness or challenges in traditional transformer, so that we have to develop this SST. Now what it will do and what it will have to perform different duties. In this traditional MVAC bus, what we have to do, the communication based upon this IEC standard and some other standards for smart communication. And second side, this SST will be giving you the flexibility of achieving or implementing low voltage DC bus separately and low voltage AC bus separately. That means you are having a multi-port, multi-voltage system at DC side and AC side also, so that you can connect DC sources and loads at one side and AC load and AC source at one side. So there is no dependency on traditional grid and no dependency on high frequency or low frequency traditional transformer, because this SST will take care of everything: isolation, voltage control, reactive power control, power quality improvement, protection system, everything it will take care, and power flow will be in both directions. This is the major advantage of this SST. So these are the main objectives or main functions which we have to perform in any electrical grid. All right, maybe transmission or maybe distribution, fault management, power management, and energy management. So all these different functions will be taken care of by this single SST, single device. All right, this we will see later on. So the main advantage of SST over traditional transformer are these: high power density, because in this we are using one high frequency transformer for isolation, so that the overall size of the system will be reduced. Around 1/10 of the size will be reduced. So the high power density will be achieved. Second is the voltage regulation. So that means you have to maintain the DC bus voltage and AC bus voltage constant under different load and source transient conditions. So this will take care of all the requirement of voltage regulations at every DC and AC bus automatically using power converters. Third, power factor correction, outage compensation, fault isolation, DC output ports are available, power quality monitoring, control and improvement also. And next, availability of DC links. This will facilitate RES integration into the existing grid. And last one is the easy interface with smart communication and smart grid network. So means whatever else we will require other than this, nothing I think. So power quality and DC port availability and smart communications, smart grid features, RES integration. So everything is covered in these functions. So this will be taken care of by single SST. And most important thing is that you should be able to flow and control the active and reactive power in both directions, because you are using storage, PV and wind as well, everything. So this is also possible with this SST. Now, as I told you that in SST we have to use one transformer at high frequency, maybe around 100 kilohertz, and sometimes it will go up to 1 megahertz also for very low power applications to increase the power density. And it is only due to the development of wide bandgap devices, because traditional silicon-based MOSFET IGBT cannot work efficiently at very high frequency of switching. So development of this wide bandgap device like silicon carbide, gallium nitride, and availability of these at high voltage also, it is a major advantage. So now around 20 kV bipolar silicon carbide device is available, which can work at around 10 to 15 kilohertz. And if you will try to reduce the kilowatt rating, then you have to go up to several hundreds of kilohertz of switching frequency, because now everybody knows that SiC and GaN devices are having very low on-state resistance, very low turn on and turn off losses. So switching losses are much reduced in this. So these are different companies which are already manufacturing this type of SiC and GaN based SST also for different ratings. Now we will see in this case why we have to take this and how much old this concept is. Now we have to see. So this SST is nothing but you can see in this picture, in this diagram, this is AC grid. Then we have to use some power electronic converters, rectifier and inverter inside this this black box. So rectification and inversion will be inside this box, and this inversion or this inverter will invert this input DC at very high frequency AC, and this high frequency voltage is given to this high frequency transformer. So this voltage at this primary of this HFT will be at around 100 kilohertz or more than that also. And the secondary side of this voltage will be again at the same high frequency signal voltage. So again, we have to rectify this and again invert it to. And if you will require this voltage given to grid, then again invert it. Otherwise, just AND this at this intermediate DC bus. All right. So this concept is not a new concept. We already studied rectifiers, choppers, DC converters, flyback, forward, and then inverters. Everything we have studied. But this is the collection of all those inverters. And while integrating together, this will be having some main problems. Then we have to solve that. And third point is that if you have to use some power converters, in that case, ultimately the power quality will be poor if you are using power converters. So the controlling of these converters will again solve that problem. So power quality will be improved in terms of power factor, efficiency, voltage sag, swell, reactive power compensation, harmonics, everything. This will take care. So this research topic I have selected before 4 years because this MIT research, they have given that this SST is the 10 most emerging technology in future. So this study they revealed in 2010 or before 10 years. So presently I am working on this area only, and this Freedom Center in NCSU, Carolina, USA. So what is Bhattacharya and his team? So they are working very hard in this area. So they have developed this SST for some applications like UPS and traction drives. So now again, these are a few advantages which I will not repeat. All right. So this is the main focus. This SST will be applicable, will be beneficial in such applications because if you are using more converters, more switches, then obviously you can say that the reliability will be poor in that case. So more switches, more capacitors, poor reliability in SST. This we have to take care. And the overall system efficiency will be also poor. All right. So, all right, we can improve the efficiency of system just by taking care of ZVS, ZCS, or any other soft switching technique. All right, but reliability is to be studied more and more. Okay, but the main advantage is that you have to use this in applications where you have to go for high power density. All right, so this is the main application area for this. Now we will come to the main structure of the SST. During 70s only, 70s, 80s, 1971 around, this was the first topology developed, single stage HVAC to LVAC conversion. All right, so they are using this high frequency link using HFT. So the size will be reduced for this, but there is no DC link here, and this was based upon the cycloconverter type of concept. So the power quality is very, very poor in this case. Size is huge, big size, low power quality, and very less efficiency also. So that and there was no DC port available here. So researchers have developed the second topology, AC, one intermediate DC, and then inverter. In this case, the isolation at high frequency is at source side. All right. And in this third structure, AC, one DC intermediate, and this is the LVAC at second level of the voltage. And isolation is at load end. All right, on back end. Okay. So these two are the different topologies, but the main drawback were again poor power quality. And second thing, there was no flexibility in integrating the different rating of RES in that case. So this fourth one is the most widely used recent SST structure nowadays. They simply use different stages. So AC to DC, with no isolation. Just you can use any rectifier, simple diode rectifier with some power quality improvement technique only. So improved power quality, active or passive rectifier. I hope means everybody studied power electronics subject, so there's no there's no difficulty in understanding all power electronic converters terms. Now after DC, this is the DC link at 1 voltage level, maybe high voltage or medium voltage or maybe at low voltage. And then this DC again invert to AC inside this block at high frequency, and this high frequency voltage will be given to this HFT, and then this HFT will transmit this power to the secondary side, and again use one rectifier here inside this block only. Then this rectifier will give you DC link voltage at another DC link voltage, and invert this if required. Yeah. If you have to integrate this DC to AC, then only you have to invert again. Otherwise, stop here and give this DC voltage to all DC loads like battery or EV charging infrastructure. So the beauty of this type of structure is that you have the flexibility. You can end at any point. All right. So this is the most commonly used topology. Now, briefly, I will just give you about the requirement of future EV charging systems. So for this case, we have to use ultimately PV or wind support with the grid power supply to the EV charging infrastructure. So now we know that if you will use this battery or storage with the grid, then the burden on that PV or RES will be less, as we can see from this diagram. All right. Then the challenges in EV technology in India, that is, you can say, a huge number of challenges it is imposing on EV charging awareness, because we have to develop some or sufficient number of charging infrastructure, charging stations, and there should be very proper monitoring and control of the number of electric vehicles connected to the electric grid or charger. So this prediction is again a separate topic of research. Some are doing in that survey study on that topic. So the availability of a sufficient number of charging infrastructure or stations at affordable price, and third one, you should not wait for a long time to charge your vehicle. All right. So these are few, and fourth one is the convenient to you. On the way, you should have some charging of your vehicle on the way, on the go. So all these things are required, but in India it will take around more than 10 or 15 years to reach to that level. So this is the charging requirements for EV charging. Charger type are available for EV battery, fast and slow or moderate. This I am just giving to you because in SST we have to develop or we have to optimize the voltage level at secondary side of the DC bus or HFT. Okay, how much voltage charger or how much voltage rating of charging station we have to implement. So to take care of this thing, we have to study this type of different charging sockets. So fast socket and slow or moderate charger. So in this case, for 50 kilowatt or 22 kilowatt, 15 kilowatt charger, 10 kilowatt charger. So these are different charger connectors available already. Voltage is different. 200 to 1000, 380 to 480, 72 to 200, and 230 voltage. And the number of charging points or connector guns are 1, 1, 1, 1, 1, 1 like this, or 3 by 3. 3 of 3, each 3.3 kilowatt each. So these are available charging guns or connectors available. So you can just classify the level of charging, number level 1, level 2, and DC fast charging. 120 volt and up to 16 amperes, 240 volt up to 12 to 80 amperes. Now we will just see this in brief. This label 1 charging. So this label 1 charging, this will give you the charging voltage of 120 volt, and you can charge up to 16 amperes only. Okay, this you can use in your house also or office buildings. Okay, so so there is no additional work required to implement this label 1 charging station. Now label 2 charging, this will be at 240 volt, and this can go up to 80 amperes. So this is, you can say, medium range of the power level or voltage level. All right. So label 2 charging have very smart design. So this is like a plug and play type of thing, and it will also help reducing the energy consumption because you are using this at a high voltage. All right. And this will also offer radio frequency type of identification or smart communication to automatic recovery and restart after ground fault interrupt or main power loss. So this is the major issue in any charging station, which can create a major fault in that. And level 3 charging is a very fast charging, DC fast charging. So if you have to go for level 3 charging, then obviously in SST, you don't have to invert that DC link output at secondary of HFT. So stop at DC level and don't invert that. Don't use any inverter. So DC fast charging at 480 volt DC and up to 125 ampere of the current. So these are the 3 different levels of charging. So just to summarize this basic phenomena. So the charging time, charging station power, energy consumption, and distance traveled. So depending upon this, just classified based upon this. So we can summarize that level 2 charging with this 240 volt 80 ampere charging station, it will give you, suppose you have to travel for 25 kilometers only in the city only. So this is the power consumption and energy consumption, and this is the charging station power in kilowatt, and the time taken to charge this battery to run for 25 kilometers is 0.75 hours only. So this type of system will give you most optimized charging station or ratings in all aspects. All right. So level 2 charging is most widely used. Now, before going into more about SST, now future need of electric vehicles with RES support. So you cannot isolate EV, RES, grid, and anything. So now it is these are talking in combinations: PV, wind, RES, PV, or the fuel cell, battery, and electric vehicles, and the power electronics. Everything is now clubbed. So these are different factors which we have to consider while designing any electric vehicle infrastructure, because it is required and standards are going on to be developed. It is not developed for electric vehicles infrastructures. Okay, so there is no fixed rules for electric vehicles till now in all aspects. It is developing. So battery charging vehicle location also, then public charging stations in numbers, capability, charging time required, everything. Traffic density, EV charging duration also, then surrounding vehicle movement. So nobody wanted to wait for charging or for anything. Nobody want to wait for anything. So people want that they have to go to charging station and within 2-3 minutes their battery should be charged completely. So you should also take care of the customer's behavior, nature also. So surrounding customer behavior also. So their nature. So grid to vehicle or vehicle to grid type of thing controlling also required, and smart grid infrastructure and smart communication protocols. So all the features should be taken care by any charging infrastructure required to be developed for future electric vehicle charging infrastructure. So just I have collected few references only, few work on SST. So in 1970s, this SST concept was used by this McMurray. So this is a well-known name, McMurray inverter. So this McMurray introduced the first SST concept in 1970s in single stage AC to AC converter. है ना? Poor power quality, poor efficiency, no poor power flow controllability, bulky in size, but he has given this concept. And after around 80s, again research has been done to develop this thing using AC to AC buck converter type of concept. In 95, you can see the huge gap in major milestones in SST research. है ना? So because there was a very means less number of high voltage, high power device available in at that time, and the major thing was the transformer. The major culprit was the transformer at working at 50 hertz. And if you will be able to operate that at high frequency, then the switches connected across the converters, across the HFT bindings, those converters should be able to switch on and off at very high frequency. And that time SCR, GTO, those were only available, which cannot work at very high frequency that time. But now, due to development of wide bandgap devices, we are having second GaN devices. So that's why this area is now accelerating. Okay. So huge gap was there in different milestones of this research. In 95, this PET is again power electronic transformer developed by EPRI lab. 96, K. Harada developed this intelligent transformer. 99, by Sadov, some different converter based upon some multi-level converter based SST topology. Then again in 2008, this is the crucial turning point in the research of SST. 2008, where this Freedom Center, Eaton Center, and then you can say this what is that? This Hart in Kiel University, Germany, ETH Zurich, GS Lai, Kolar, and Joshi, and those people, Fred Blabjerg, those have started means at very large scale for development of this SST. So since last 12 years only, this picked up. All right. So this was the first SST developed in 1970s. It was used for traction drives. In traction drives, we know that this overhead catenary is coming in the engine at fundamental 50 hertz frequency or 60 hertz, you can say. And this transformer is again used bulky, heavy transformer, rectification and inversion, and then drives control is there in traditional traction drive system. But in this SST-based traction drive system, they are using this fundamental voltage frequency from overhead category, then AC to AC conversion. So this is a matrix converter, or you can say cycle converter, AC link only. This will only increase or step up the frequency only to some several kilohertz. So this high frequency is given to this transformer. So this is the one concept here in 1970s. So we know that if you will provide or supply or feed a voltage at very high frequency, then obviously the size of the core of the transformer is getting reduced. All right. So this was the basic concept. Okay. So this concept used for traction drives. Now, so many patents were available in 70s based upon single stage SST concept. So this is having poor power quality and so many drawbacks. Okay. So I will not cover more literatures on traditional SST. This is the modern SST concept used nowadays. Okay. So what it is giving you. Now we know that in SST, this will be having this fourth block diagram, this is, topology: AC to DC, DC to AC, and again AC to DC and DC to AC. So these are the different conversion stages which we have to implement. So see this, you are having one three-phase AC grid, all right, and in each phase you are using some modular type of structure, modular in nature. So this is one module. In this module, you are having one rectifier, one DC link, and having one inverter. All right, just a minute. I want to take just questions, then you can just write on the chat box. So I will give you the answers. Okay. So this is, you can say this module number 1 is having all converters in single module. So rectifier, inverter, this will invert at high frequency voltage, give it to this HFT. Then again rectification is there, so DC. So AC, DC, DC, AC, AC, DC. So you are having this common DC bus here. So, and in every phase, you have to connect, integrate all such modules. All right, 3 modules, 3 modules, 3 modules in each phase. Now, the beauty of this type of structure is that you are having flexibility in your hand, so that if some fault occurs in any converter or in any device, so that can be replaced or bypassed by the controller, DSP or FPGA very easily, and this will maintain the power supply to the load or grid, all right, without affecting the, means you can say, output or product of the industry. So this is the beauty of this type of structure, and it will depend upon you how many stacks or modules you have to use per phase, depending upon the rating, current voltage power rating of the system. All right. So this is the phase stack, converter cell, DC-DC converter, and protection at LV and MV side, and everything is inside this. Now we can have one flexibility that every output of this can be given to separate AC also. Otherwise, just connect this in input series, output parallel, or input parallel, output series type of connections, depending upon voltage current requirement of the load side and available rating at source side. Okay, so this is the major advantage of this type of application. And it is not possible without using multi-level converters, not possible, because otherwise you have to go for very high power rating devices. So I will not go to in more detail about that thing. This slide will give you the feature idea about the size reduction. This I have taken from this IEEE IES magazine in September 2016 for the same power rating for the same application. This is the size reduced with as compared to traditional 50 Hz transformer. It is for 20 kilohertz transformer. If you will increase the frequency of operation of this transformer, then it will still go, it will reduce the size of the transformer core. All right. Now we will come to the research type of research contribution from my side. So this is the component of SST. So now it is more clear picture. AC grid, one rectifier. It is not a simple rectifier. It is a improved power quality converter used at this stage, so that this will take care of supply current THD, supply current power factor, and this will also maintain this DC link voltage at constant level. Under different backend or DC or load and conditions, and under all input side power quality problems, sag, soil, and other things. So this is improved power quality converter, having again efficient and high power density converter. Now this DC link is at 1 voltage level like MVDC, around 10,000 volt DC. Invert this, use 1 HFT, again rectify this, use second DC bus here at LVDC ratings, and if required then invert this to AC, otherwise stop at LVDC. Okay. Now out of these converters, the major component or most important component of this SST is this middle stage. This is the SST basically. DC to DC conversion. So this is the most important stage of this. So this is implemented like this: input DC, output DC, 1 H bridge common to both sides of the transformer, and this is a HFT working at high frequency, having a turn ratio 1:10 or 1:1 also sometimes in some applications. Now we have to see how we can control this SST or different component of SST. So to control this SST, these are the 4 objectives which we have to meet. All right. It should be able to provide a seamless power supply to end users with good reliability. All right. This is the major objective, prime objective. It should be able to provide voltage balance control at each DC link. It is a very difficult task to make balanced voltage in such type of applications. Here, in such applications, which give you so many advantages, but some point you have to take care, because slight mismatch in the voltage at each DC link here or here will create huge problem of power quality, harmonics, and everything, or losses, stress on the device also, everything. So we have to take care of this thing. We have to balance the voltage across each DC link very effectively and accurately also. All right. Then to provide a simplified control scheme, okay, achieving better transient and steady state response also. It is common in all applications. And next main objective is that it should be able to provide active and reactive power flow control in both directions and capable of mitigating the power quality problems. So in the last point, you can see all things covered. You know? So active power control, reactive power control in both directions, power quality problems mitigation. And other than this, power electronic engineers does not have any more expectations from industry. You know? So these are the main, you can say, main expectations coming from industry from power electronic engineers. Now, based upon this discussion till now, we can summarize that these are the major challenges in SST. Okay, so depending upon the huge number of power electronic components, converters. Second, depending upon HFT used inside that, so we can say that it is less reliable. It is having less conversion efficiency overall as compared to traditional low frequency transformer based grid. System is a little bit complex. And last one is the we have to make it compatible with existing protection system. All right. So these are few major challenges. Out of these, efficiency part you can improve using SiC or GaN devices or ZVS, ZCS, or any passive components. Reliability, we can improve by reducing the total number of devices in the same converter. Like some recent topology of multi-level converters with less device count, which will give you improved power performance. Okay, complexity is not a problem nowadays. We can cope up with this thing. And protection, again, another area. So power system person can do for this case also. So these are few companies which are developing this SST, Uniflex, EPRI, G and ABB at different ratings, voltage ratings. All right. And operating frequency of transformer, they only went up to 20 kilohertz, because again problem occurs if you will increase the frequency of the voltage given to the transformer, then the power handling capacity will be reduced. Okay, so you cannot go beyond this for high power ratings. Yeah. So this is the major issue. So based upon these different performance parameters, these companies developed these SSTs. So they achieved 98% also. Okay, this GE for 1 MVA only. Power rating is very less, you can see here. If you will go for a high power rating like this 300 kVA, then 92% is there only. Okay, so these are few challenges, right, in SST, but it is the future of smart grid. So this SST is looking applications in subsea area, marine, traction drives, smart grid and EV. So these are very relevant applications for SST. Now this second part I will focus on development of this main component of SST, that is the dual active bridge. All right. So after having this brief overview of on SST, SST is the future of smart grid or future of electric vehicle charging infrastructure and all such applications. And this DAB is the major component of this SST, DAB. So this picture will give the basic overview of AC grid, then one common AC bus, then rectifier, common DC bus, at one voltage, then DAB, dual active bridge, having two converters, DC to AC, then HFT, then AC to DC. Okay, so then second DC bus is available here, then rectifier or inverter. Okay, and all converters should be able to flow the power in both directions. All are bi-directional power converters. Okay, now wind, solar, battery, supercapacitors, fuel cell, any RES can be connected at one common DC bus here through some converters and their proper control. Okay, so all these converters and converters in SST all should be knowing what is happening at other side, so that all are closed loop control. So for a proper energy management system, EMS, all should be having very fast controller like FPGA, all right, to take care of the future smart grid, which will be having smart sensors, smart communication at very fast rate. Okay, and the second DC bus can be connected to different DC loads, traction drives, EV charging, or any domestic loads. And if required, then invert to AC, otherwise stop here. Okay, now we will come to this DAB part. So this DAB for SST is having this type of structure. This is developed by this Freedom Center in NCSU, Carolina, USA. AC, passive filters, then one rectifier, then one DC bus, one inverter here, This will invert this DC into high frequency voltage. HFT is there. Then again rectifier here, then DC bus, then inverter, again passive filter, and give it to another grid, AC grid. Okay. So this bus is around 98.5% efficient using the latest SiC or GaN device type of converters. Okay. So again, we know that the power flow should be in both directions. In DAB, we have to use one H bridge at one side of HFT, second H bridge at second side of HFT. And this type of converter system, it is nothing but a switch. DC source, one switch, one inductor, additional leakage inductor, second switch, and second DC bus. So this voltage is coming at this VP. So this is a stepped voltage. Vs is again stepped voltage. And in between, there is one inductor. So this is the equivalent circuit of this DAB. So Vp and Vs are the converter terminal voltages, and N is the additional leakage inductance. All right. So what we can say from this, if you have to flow the power, you have to flow the power from left to right, then Vp should be more than Vs. And if you have to flow the power from right to left, then Vs should be more than Vp. So this is the simple concept we have to use. And how we can implement this thing? Just by simply controlling the phase shift angle between this Vp and Vs. All right. So this phase shift control is the main objective to change the power flow direction. Okay. So to change the phase shift control, these are the three major control techniques available: SPS, single phase shift, extended phase shift, and dual phase shift. These are the traditional control techniques. In SPS, just see here. This is V1, V2, Vp and Vs. So Vp and Vs are these blue and red lines. Vp and Vs are the voltage at primary and secondary side of the HFT. Okay. So what it will do? So they are having some phase shift. So from the basic circuit theory law, we know that this current through this inductor will be constant if these two voltage across this inductor will be constant. And if there is slight difference between those two, or varying voltage is applied across those two terminals of this leakage inductor, then current will be rising or decreasing depending upon the rate of change of the voltage across that inductor, one and other side. So this is the leakage current inductor, current through leakage inductance, or you can say current through transformer only. So this profile of this, and this is the VL, board leakage inductor. So what we can say from this, that the power quality of the or profile of this current through inductor or transformer is not good. This will be more near to square wave. This is the only control variable, phase shift between these two voltages. All right, this DTS. Okay, so this is the major or control parameter here. Now in EPS, we have inserted one external or additional phase shift angle here at the secondary or falling edge of this voltage pulse here, D and D1TS. So independently they can control. So the or current will be input in that case. And third is the DPS, dual phase shift. In this, they are using one DTS here. The phase shift between this primary and secondary voltage, fundamental, only fundamental. Okay, this dotted is the fundamental instant. Okay, so this and this DTS, then at falling edge of this voltage, D1TS, and falling edge of this secondary voltage, D2S. So like this, they have inserted 3 degrees of freedoms. So we know that if you are having more control degree of freedoms, then you can control the performance of the system in some effective manner. And this is the power flow equation derived for this DPS, depending upon this phase shift angle phi, and phi will depend upon DTS. Then now I will come to the proposed DAB converter, which we developed in the laboratory also. So now in this DAB, we are using only two-level inverters here. Two-level inverters at both the ends. Okay. So now everybody is working on multi-level converters. So because the two-level converters are having some drawbacks, and the main drawbacks of two-level converter is number one, THD or harmonics are more. Number two, you have to switch the MOSFET IGBT at high frequency to reduce the THD, but at the same time you are adding more switching losses. And number third, main important drawback is that you have to use very high rating devices to develop high power converter, or you can say stress of voltage across the single device is more in two-level converters. So to take or to mitigate those drawbacks in two-level converters, we have to go for multi-level converter based system. So this is a T type of inverter. All right, one H bridge and one bidirectional switch. All right. So this topology is already available, but that was not used in DAB or SST before this. So across HFT, because you cannot use any topology in any application or any converter, there are some drawbacks, some type of modifications in topology and control you have to incorporate to fit any topology or control technique in your application. Okay. So this is the proposed symmetrical bidirectional dual active bridge topology here. So one DC link voltage, one proposed T-type inverter converter, one inductor here, one HFT, then second similar T-type converter here, and second DC bus. So it is a symmetrical configuration. So the overall harmonics will be reduced, and second, this will require HFT also. So the size of this will be also reduced, and it is 5-level. So just by adding one switch here, it is 2-level, so 2 to 5 level. So just by adding one switch additionally, you are able to implement 5-level output voltage. So the stress of the voltage across the switch will be reduced, harmonics reduced, and power flow in both directions is possible in this case. It was not in previous 2-level case. So due to the use of this bidirectional switch, the power flow can be reversed also. If you are using photovoltaic array at this V2 DC link voltage, then or battery here, or V2G or G2V type of applications in electric vehicles, then the power flow should be from right to left also. Okay, so you have to use all power switch bidirectional. Okay, so this was first presented in ICON Lisbon, Portugal. This is the major or basic concept of control technique here. Now we will see it in more detail. In this control technique, now it is a 5-level inverter or converter. Now in this case, you can see this red line, dotted line. This is the fundamental primary voltage across HFT. Okay, fundamental. Okay, or you can compare this with a 2-level square wave, this red one. Okay, just a 2-level inverter waveform or fundamental voltage of VP across HFT, this red one. Now this red one, actually you are achieving 5 levels. So this red one is the actual voltage at primary of the HFT. So this red one. So label 0, then label change, label 1, again label change, label 2. So we are having this full voltage, label 1, label 2, label 0, then -1 and -2. So we are having total 5 label voltage in one half cycle. All right. So that's why it is 5 label inverter or converter. Okay. Now in the same way, you can just see this blue line for secondary voltage across HFT. See the secondary dotted line. This is blue dotted line. Okay. So this is the fundamental secondary voltage, or you can say this is the 2-level square wave voltage in ideal condition in traditional 2-level converter. Okay, because we have to compare its performance with traditional 2-level converter, that's why we are using this as the base, okay, or reference. Again in the VS you can see this blue line, top one, this label 1 to label 2, label 3, label 4, label 5. So 5 labels. Okay. Now, as we have discussed that if you are having more number of degree of freedoms or control parameters, then you will be able to control the power, current, voltage effectively, all right, over wide range with good power quality also. So in this case, in previous examples, we have seen that we were having only 3 control parameters, one here, one here, one here. Now we will see in this example, we are having one phase shift angle delta between fundamental primary voltage, this red one, and fundamental secondary voltage, this blue one. So this delta, number 1 control parameter. Now second, this is the reference fundamental zero crossing instance, this dashed red line. Label is there, label changes at this instant. So just at this instant, so this 511 is the angle duration between fundamental zero crossing and first label crossing or label changing of VP. So this instant, this one. Okay, so this 511, then 512, this label 1 is there till this instant. So at this instant, label change is there from this label to this level. So the phase shift angle between this fundamental VP voltage and second label change instant, this one. So 512. Yeah. So delta, then 511, 512 are control parameters. In the same way, you can just have a look on this VS, this blue line. So fundamental voltage of this blue line. Okay. So this 521, label change at this point. So 521, label change at this instant. So 522. So in this way, you can have total 5 degree of freedoms now in all. So this whole system is divided into, whole waveform is divided into total 16 modes. So mode number 1 to mode number 16, or times T0 to T16. And according to this, just highlight this and just obtain FFT of this waveform. Find out FFT of this VP and VS, and then draw this VL and IL across inductor, leakage inductor. So you can see this current profile. It is much improved as compared to this one, right? Okay. So this is the basic idea about this proposed DAB converter, and this is the switching table we made Dharmendra Yadav, my PhD student, he did this work. So different switching states are derived to achieve different levels, and that Dharmendra, my student, doing PhD since last 3.5 years. So he developed this equation mathematically. So this power flow equation for this proposed T-type symmetrical to DAB converter. So this will depend upon now all 5 parameters. So after FFT of VPVS, then current, then find out power. So this will depend upon all 5 control phase shift parameters, and leakage inductance, which is fixed for a fixed converter. Frequency of F is the frequency of switching, and 2 DC link voltages. All right. So just by changing the phase shift angles 511, 12, 21, 22 or delta, you can have a power flow positive or negative. Okay, in this way. So it is also possible here. And each phase shift angle is having its own range or limitations. So these are few results in MATLAB simulation for 2-level case and for 5-level case. So these 5 phase shift angles are different for this case. So we are having this IL. It is much improved than this IL for 2-level case. This peak current ripple, this sharp peak is not present here. Harmonics are reduced in this case. All right. And this 100 peak. So peak current is 100, but here 50 due to the use of multi-level converter in this case. For different phase shift angles, all 5 phase shift angles, we are having different current profiles. All right. So we can have this. So there is one way we can optimize those 5 phase shift angles to give you optimized performance. It is maybe one research area we can take for future work. Now this is the hardware developed for this symmetrical T-type DAB topology. So this work is already accepted in IETP already. This work. This is the table for some ratings of the converter. In lab prototype, we used FPGA for fast switching, and these are few hardware results for this for different power ratings. All right, and for different phase shift angles. Okay, so we can have a different profile of the current as well. So we can select phase shift angles appropriately depending upon our requirements. All right, and this is the second investigations. So loss comparison. So overall losses are much reduced as compared to traditional 2-level converter with different optimized, you can say, phase shift angles for this. And so from this discussion now, because I have just skipped some content to take care of the timings. So now what we can summarize for this SST, that this is the distribution grid. This is single SST. Then low voltage AC bus is there here, and from the same SST you can tape this low voltage DC bus here separate. So separate DC and AC bus are present here. Storage, PV, wind, electric vehicle chargings, so many households applications can be clubbed together, all right, in single SST. So this I have taken from this IS magazine from in 2016. But in this case, what we can do, that is power management, control power factor, change control customer voltage, provide DC power, LVRT, islanding detection and reconnecting. All these functions should be performed within few microseconds. This we know already. Second point, fault management, current limiting, disconnecting, reconnecting the faulty part of the grid should be performed within few few milliseconds only. Then third, energy management. Okay, so monitoring, controlling, dispatching the power via microgrids. So all these can take few minutes. Okay, no need to perform these in within few microseconds or nanoseconds. And demand side management, DSM, this can take some hours, hourly, 2 hourly, 4 hourly, week or 7 hourly, daily, weekly, like this we can do. So all these functions will require sophisticated and fast controllers, some fast and some may be moderate. So you can optimize the use of the controller speed also in this SST. So, and everything will be very, very achievable with effective and accurate and efficient way by SST, because each of these will require some power converters. And SST is nothing but the power converters. So there is no need of additional equipments, power converters to achieve all those objectives. Yeah. So this is the very, very prominent area of research for future smart grid, which will include so many RES, so many storage, electric vehicle charging infrastructure, and so many unexpected highly nonlinear loads. Yeah. So this SST is the most prominent, you can say, converter, or you can say contribution of our electronic engineers towards future electric energy hub. Okay, so these are okay. I should mention the name of the students which have helped me. So Sai, Dharmendra, Deepesh. So they are PhD students and they are also working under my project sponsored by DST on the SST development. So these are few publications also coming out from these this work, and some are in some journals, some are in conferences. And thank you very much. And if any questions, then I will be more than happy to give the answers. I hope I have finished timely.
Yeah. Your timing management is quite good. Now I request all the participants, if anyone has any query, please may ask. Session is open for discussion. After this session, Dr. Amit Jain from IIT Delhi, he will join at 3:30. So we have the 10 minutes, we can discuss. Please.
And Arvind sir, I hope participants got something from the lecture. I hope.
Yeah, definitely. So now that Madam C is asking something, please.
Yeah, excuse me, sir. So that's regarding the switching losses only, because the SST efficiency is said to be around 98, like that. So how it is accounted in that switching loss? Because high frequency switching, it should justify it. No?
Okay. So as I told already that in this case we are using so many converters. So the obvious question is that the overall switching losses will be increased because you are using a huge number of MOSFET IGBTs. And we know that turn on and turn off instance will take some switching losses. So in that case, the efficiency can be only improved by two methods. Number one, we can go for soft switching techniques for the converters. And number second, we can use some passive components, but it is not suggestible because it will add some more passive components. So the power density part will be missing in that case. So this is the main thing. And third one is we have to go for wide bandgap devices, 6 or GaN devices. So this will take care of the efficiency.
Okay, sir. And what about the cost of, because we are just replacing the conventional transform with this one, no? So how it will be?
Cost, see, cost wise means it is, you can say it is a little bit more costly because you are using more converters and you are using a high frequency transformer whose core you have to make by not from iron core. We have to go for not for ferrite core as well. We have to go for some recent core material having very high permeability, like a sandust core, है ना? Or you can say like a planar transformer. So this type of latest technology we have to use to take care of that, but it is more costly. So cost obviously will be increased cost, but the cost
Okay,
is
thank
not
you,
the issue if you have to go for a high performance.
Go for it, yeah, because in future technology is of SST. So
Yes. Just now
thank you, sir.